Welcome to Build Your Own Solar System Part 2. I'm Derek Wallentinson, and in this sequel to the construction of your system, I'll show you how it works and how you can learn and teach many basic characteristics of a solar system. In your solar system, the straw holds the larger body. Is this the sun? To the smaller body. Now, in the real solar system, what force acts between the two? Of course, it's gravity. It acts in a straight line between the sun and the planet. In part 1, we found the balance point of your system. In astronomy, the balance point is the center of mass of the two bodies. When you use the toothpick through the balance point as an axis and spin the system, you are creating two circular paths. What would these be called by astronomers? Yes, they are orbits. As I spin the system, which one moves faster, the sun or the planet? The planet moves faster. Which one moves the greatest distance? Again, the planet. Which one has the longer period? Tricky question. Observing carefully, you can see they both have the same period. Our little model is a giant at explaining a lot of solar system dynamics. Let's add in another concept to make it even more powerful. What does motion do to sounds? Here I have a bell of a pure tone. Listen to this high note from this perfect bell as I hold it still. What happens when I move the bell to and fro? The pure tone goes away. It changes. You can definitely hear it. It goes to a lower note as it moves away, a higher note as it moves closer. Here's a drawing with the bell replaced by a fire engine with siren. In front, the sound waves are crowded together. In back, they are stretched out. In front, you hear more waves per second, a higher note. In back, you hear less waves per second, a lower note. Even if you've never had a physics class, you've probably heard of the Doppler effect, and certainly you've experienced it in life. So how does this relate to the model solar system? It relates because light behaves just the way sound does and has a Doppler effect. It relates because in astronomy, what we observe is light from objects like the sun. So when the sun and its light is approaching us, all the wavelengths of light become just a little bit shorter wavelength light is blue, like the flashlight. And the light is Doppler shifted towards the blue. As the sun is moving away from us, what happens is the light gets redder by a little bit. Now the eye can't see this effect even using a telescope, but instruments can, and they measure the wavelengths or spectrum and readily detect the spectral Doppler shifts. Looking at the spinning model, which one has the greater Doppler shift? The planet, because it moves faster. And which one emits the most light? The sun. The sun is millions of times brighter than the reflected light of a planet. Now, if you're close to the model and can see the sun or star separate from the planet, You might be thinking, so what? I don't need the shift to show how it's moving. That's the case when we look out at our own solar system. What if it's so far away you can't see them separately? All you can see is a point of light? Now this is the case when we're looking at other stars. Even the nearest are hundreds of thousands of times farther away than the planets. We might ask, are there planets around that star? How would we find out? Now all we see is the point of light. And the star is millions of times brighter than a possible exoplanet. What to do? Look at the spectrum of light from the star to see if it has Doppler shifts corresponding to orbital motions of possible planets. Wow, we've come a long way with our little baby. Let's go farther. Since a star, or the sun, is so much brighter than a planet, what if the planet crosses in front of the star? It blocks a little part of the star, right? And if we measure the light's brightness, we might see a dip at that time, right? Now looking at that distant star, we might ask, are there planets around that star? How would we find out? By looking for dimming of light from the star corresponding to orbital motions of possible planets. Now I've shown you how your model solar system can reach out to explain how astronomers are finding planets around other stars. This is how earthbound telescopes and those in space, like Kepler, TESS, and Webb, are finding exoplanets. I won't go any further. However, you can also use your model to help explain even more exotic systems, like binary stars and pairs of black holes and neutron stars. The sky is not the limit. I'm Derek Wallentinson. Till next time, may your skies be clear and dark.